as astronomers, we're very fortunate that it has huge public appeal. And secondly, it's easy to understand the questions that we're addressing. Where did the universe come from? What's its fate? Is there life elsewhere in the universe? What is a black hole? So the questions we're asking now are really quite simple. When did cosmic dawn occur? Was it a gradual, slow event, or was it dramatic? Did the whole universe switch on in starlights sort of in a short period? And perhaps the most intriguing question, given James Webb is working so well, do we have the capability to recognize a first-generation stellar system? That is an object that's pristine, chemically pristine, that is just emerging from darkness.
Any sufficiently advanced technology is indistinguishable from magic.
Welcome, everybody, to an exciting episode, a cosmic episode, going back to the very dawn of the universe, featuring a renowned cosmologist and professor of astrophysics, and that's Professor Richard Ellis, who is in the Faculty of Maths and Sciences at University College London, where I've been for a little bit. And he is known the worldwide for his contributions to our understanding of the universe. We're using observational cosmological techniques, telescopes, computers, a massive brain that he possesses. And that's with observations. And a lot of times we've had on past guests on the show, such as Neil deGrasse Tyson and Martin Rees and others. This is very different. He is actually a user of these great enormous instruments, including the ESO's VLT, the Twin Keck telescopes, the Atacama ALMA instrument, and many others. And of course, we'll talk about the latest and greatest developments with Webb and Hubble and so forth. But he is really on this podcast today because of a connection that I had to him through my colleague at the University of California up the road in Los Angeles. And that's Michael Rich, who's kind enough to put me in touch. And Michael, I think, has the distinction, Richard, correct me if I'm wrong, but I think he was Neil deGrasse Tyson's thesis advisor.
That's right. Yes, he was, in Columbia University.
At Columbia, that's right. So there's a connection to past guest Neil deGrasse Tyson, and he is the reason. So thank you, Michael. I hope you're watching this and enjoying this. Thank you for your generous introduction. We have the opportunity to talk about this phenomenal new book that is, I don't know how you did it, but it's a page turner. It's something that's enjoyable to read for professionals and for lay people alike. And you've just come off a mini book tour of Los Angeles, the highlights of hobnobbing with celebrities and benefactors at Caltech and elsewhere. And that has to do with your past, where you used to be a member of the teaching staff. And we crossed paths briefly, but neither one of us remembers the other, unfortunately. But this book is really just a delight, and you're to be congratulated, sir. I want to start, as I do with all my esteemed guests who have done the heroic effort of writing a book, a popular level book that's understandable by anybody with a curiosity and imagination. And I like to judge books by their covers. You're never supposed to do it, but I'm going to do it because what else, dear God, can we say about a book until we've actually read it, as I have in multiple formats? So, Richard, take us through. Help us judge the book by its cover. Explain the title, the subtitle, and
the picture.
The cover image. Yes, sir. Take it.
All right, let's go. Okay, so the title is When Galaxies Were Born. So the idea is that we would probe the universe back in time and see whether we could actually directly observe the first galaxies emerging from darkness. That moment is called Cosmic Dawn, and that's the subtitle of the book, The Quest for Cosmic Dawn. And it's a story of really an adventure, scientific adventure, that's taken about 50 years of beginning to look back further and further back in time. Now, the cover picture itself is the observatory on Mauna Kea, the top of the big island of Hawaii, which is the best Northern Hemisphere site in the world for optical astronomy. And it shows the array of the Twin Keck telescopes, which I used when I was at Caltech, the Japanese Subaru telescope. And it's a photograph taken actually not at dawn, but at sunset, or just before sunset. But the sky behind it gives the impression of the dawn of light in the universe. And there's a big, beautiful picture of a galaxy on the top just to make it look very beautiful. So it took some effort to convince Princeton University Press. They came up with a number of covers, but I insisted it had to have an observatory in the foreground so that everybody knew this is to do with observational astronomy. And I think it's a striking cover. You know, I'm not afraid of people going into a bookstore and judging a book by its cover. So I spent quite some time assembling this photograph. Obviously, it's a montage of an actual photograph taken from Mauna Kea with galaxies in the background.
That's right. And the book covers so much. And what I love about it in particular is there's so much care and attention paid to observers and what observers have done. And the quest is sort of underpinned by the advances in technology ranging not since, you know, the beginning of time or since this guy over here, which I always have a finger puppet handy of my hero, the very first observational astronomer in history to use a telescope. And that's, I don't know if you recognize this guy, it's Galileo Galilei.
Yeah, right.
And he said something very interesting, Richard, in Sidereus Nuncius, Starry Messenger. He said the following. He said, these sights, which with the aid of the perspiculum tube, namely the telescope, the spyglass as it was known, are here heretofore revealed in such great detail that the wordy arguments of philosophers are utterly destroyed, meaning that people would speculate about, well, was the Milky Way comprised of stars? Were the Pleiades purely stars? Was the moon completely crystalline and smooth? Talk about what a telescope. Well, actually, I want to ask you a first question. What was your first experience like when you looked through a telescope?
Well, I made my own telescope as a child, and the first thing I looked at was Jupiter and its moons. But what struck me, actually, first of all, was the colors of stars. Now, if you walk down the street, and look up at the night sky, you can see the stars. And if you're very perceptive, you'll see that the stars have colors. Some of them are blue, some of them are red. And that became much more evident when I had my own telescope. It was a very modest telescope, 4 inches. I was living in North Wales where it rains all the time. So, it wasn't an enjoyable time to go out observing, but I was fascinated. And I was so hooked on astronomy, I couldn't wait till it got dark. In the afternoon, I was thinking, what time's sunset today? And I can take my little telescope out. So the colors of stars relate to their temperatures. And, it's that connection where you make an observation and it puzzles you. A star shines. Why aren't they all the same? And the answer is some of them are massive, some of them are less massive. The massive ones are shining very brightly and they're hotter, and that leads to bluer colors. The cooler ones are less massive and they shine in red light. So, as a 12-year-old, an observation like that leads to a question. Well, what does all this mean? And so that links back very much to your Galileo quote, I think.
Yeah. And I always like to point out that when you think about scientific exploration and learning and education, you cannot feel what it was like for your countryman, Peter Higgs, to know that the Higgs boson had been discovered. He couldn't look into the Higgs, into the LHC and detect it, nor could anybody, because it took years to compile the data. The data are not particularly viscerally inspiring, but with a telescope, you can reproduce with a tiny little telescope like this one, which I always keep with me at all times. You can see the exact same sights that Galileo saw, no matter where you are on Earth, no matter what time of year you're looking, and even in the midst of a big city, you can see the same sights. But more than that, Richard, you can feel what Galileo felt. And no other scientific exploration is that possible. You can't do it even with a microscope, but everybody can viscerally appreciate the thrill of discovery. And I think that is a unique aspect of astronomy that we don't, quite frankly, take enough advantage of, because we have this wonderful ability to convince people of the joys of astronomy. So anyway.
I agree. Well, let me just comment. We're very fortunate as astronomers. We're very fortunate that it has huge public appeal. And secondly, it's easy to understand the questions that we're addressing. Where did the universe come from? What's its fate? Is there life elsewhere in the universe? What is a black hole? And, compare that with biology, where there's a lot of jargon that you have to learn in order to understand what a biologist is doing in his or her research. So recently there was a survey of people in professional careers, engineers, mathematicians, economists, or, doctors, and they asked them when they were young, when they were children, what inspired them to go along the careers they have. And in many cases, it was astronomy, because it's such an accessible science, and the curiosity is very popular and wide-ranging in the community.
That's right. And we need to really be aware of that. And the biggest picture, you and I were chatting briefly before I started recording about the dearth of books other than cosmology, astronomy, or particle physics and so forth. And I've had on some great guests, and we'll have on many more from, that have written books about condensed matter physics or biophysics and things like that. A lot of people have talked about the consciousness in the brain from a quantum mechanical perspective, including your countryman, Sir Roger Penrose, many times on this podcast. And it's so delightful, but nothing really captivates the mind like astronomy, because we're all born with two refracting telescopes embedded in our skulls. And as we get older, we
can observe directly. Yeah. Right.
That's right. So, and even the cover, image, we can see the most distant object visible to the naked eye is the Andromeda galaxy. And that galaxy has light that left it when Lucy was walking about the Serengeti plain. So these things just boggle the mind. And then, of course, in the later, in more recent times, people have speculated about the existence of other universes, which can come into play as we learn more and more about the physics of the extreme early universe, perhaps through inflation. So, Richard, you've been kind enough to provide a set of slides, which we will overlay, and you presented these in a public level talk. And I don't want people. Richard is one of the most distinguished professors on Earth and has the medals and so forth to prove it. But this talk you're going to present is suitable for the public. So do not be intimidated. I love to bring the most advanced knowledge to my audience because they're the brightest minds in the known multiverse. But Richard is going to present a set of slides that he's prepared that loosely trace the arc of this book. And then at the end, you and I will conclude with some discussions about the future of the quest for cosmic dawn. So please, Richard, if you wouldn't mind sharing your screen and starting your PowerPoint discussion.
This image here is one of the deep images that was first taken with this new telescope, the James Webb Telescope. And it is a truly astonishing image. What you see, firstly, is a star in the Milky Way, very, very sharp. You see a cluster of galaxies that are these objects in white that are all at the same physical distance. But you see also these distorted red objects. Many of them are arc-like. And these are background galaxies whose light has been magnified and stretched by the material in this foreground cluster of galaxies. And this image was presented in July of last year as the first exciting science image with the James Webb Space Telescope by President Biden. And, the advance here is that these objects are very, very distant. And if we look to great distances in the universe, we look back in time. So astronomers are very special in that they can time travel. When we look deep in the universe, the light has taken such a large fraction of time, of the fraction of the age of the universe to reach us, that we're seeing the universe in the past. And so clearly we have the capability to time slice the universe. If we can determine the distance to a remote galaxy, we can calculate at what time in history we are observing that object. And by looking at galaxies at different distances, we can recreate, astonishingly, the past evolution of the universe. And obviously, to do this, we need a marker. We need some measurement that tells us how far back in time we're looking. And the key to doing this is the expansion of the universe. Now, people probably know that the universe is expanding, but I'm sure you remember, Brian, it's incorrect to think of the expansion of the universe as galaxies moving as projectiles through pre-existing space.
Right.
It is actually space itself that is expanding. And so, for example, when a light ray leaves a galaxy over here, and this blue light ray travels towards the Earth, the distance is so vast and the time it takes is so long that by the time the light ray reaches us, the space between these two galaxies has been stretched. And here's the key point: the light ray itself has been stretched as well. And if we can measure this stretching, which we call the redshift, people have already heard of this term, the redshift, that is the stretching of the light ray, is actually the factor by which the universe has expanded since the light ray was emitted. So if we have some idea of the history of the expansion of the universe, then we can convert this measured redshift into what astronomers call lookback time. Now, this is a very important and very useful concept. Lookback time is how far back in time we're looking when we observe a distant object. And over the last, say, 20 years or so, the partnership between the beautiful Hubble Space Telescope images and ground-based telescopes has allowed us to piece together a sort of picture book history of the universe back to when it was about 1 to 2 billion years old. So the universe today, we think, is 13.8 billion years or so old. That's about 3 times older than the solar system or the Earth. And I just, for schematic purposes here, I've just shown some beautiful nearby galaxies. This one's what we call an elliptical, as a ball of stars. All of the stars are the same color. This is a spiral galaxy like the Milky Way. You can see it has a nucleus. It's got beautiful spiral arms, got a little companion. And as we go back in time, you can see galaxies at when the universe was about 40% of its present age. You still see objects that look like this elliptical. You still see galaxies. Maybe they're not as elegant as the spirals that we see today, but they do have a nucleus and a blue disk-like structure.
That's right.
But look at this. When we go to when the universe was only 1 to 2 billion years old, so that's about 10% of its present age, the galaxies are physically small, they're not symmetrical, many of them have multiple components as if they're coalescing. So over the last 20 years with Hubble and telescopes like the Keck telescopes in Hawaii, we've got a sort of general view of the assembly history of galaxies. And my book describes this progress in some detail. But the real challenge we now face and the excitement in the subject is probing even earlier to when galaxies first emerged from darkness. So this is obviously a cartoon. So time is running from left to right. This is the Big Bang, the glow from the Big Bang. We call that the microwave background. I don't have to explain that to you, Brian. You're an expert in this area. As the Big Bang, as the universe expands from the Big Bang, the gas cools as the universe expands, and eventually the hydrogen atom forms for the first time about 370,000 years after the Big Bang. But the universe is very dark. We call this period the Dark Ages. Astronomers, love this word dark, because it airs you've all heard of dark matter. Maybe you've heard of dark energy. This adds an air of mystery to the subject that is very good in fundraising. But the Dark Ages here eventually come to an end because the gas clouds collapse. And as these hydrogen clouds collapse, they get hotter in the center, just like a bicycle tire gets hot when you compress the gas in pumping it up. And eventually the gas clouds become hot enough in their cores to ignite nuclear fusion, which is, of course, how the sun shines. And at that moment, the universe is bathed in starlight for the first time. Now, many people think the Big Bang is the biggest, epoch in the history of the universe, and it's certainly a very important and mysterious one that we don't completely understand. But I would argue that cosmic dawn is equally important milestone in cosmic history, because stars are producing the elements, the chemistry, the chemical elements in the universe. At the time when these first stars form, there is no carbon, there's no oxygen, there's no nitrogen, silicon, iron. All of these elements that we see around us today, including the material that makes our bodies, the calcium in our bones, the iron in our blood, is all synthesized in stars. And that all began at cosmic dawn. So in some sense, cosmic dawn is the beginning of you and me. It's the beginning of the process that leads to life. So understanding cosmic dawn is really important. Now, over my career, we've probed to successively greater distances. One starts in the 1960s. This is a graph of this redshift. If you prefer, it's the age of the universe at which the galaxy is being observed. And you don't even have to notice the numbers. You can see as a function of publication date, as we had more powerful telescopes, we started probing galaxies when the universe was younger and younger and younger. And already, since the launch of James Webb Telescope, there's been in just 6 months so much progress in understanding and extending this frontier that it's very, very exciting. So the questions we're asking now are really quite simple. And that's, I think, the beauty of astronomy. You know, you don't have to have a PhD to at least understand what we're trying to do. When did cosmic dawn occur? Was it a gradual, slow event, or was it dramatic? You know, did the whole universe switch on in starlights sort of in a short period? And perhaps the most intriguing question, given James Webb is working so well, do we have the capability to recognize a first generation stellar system? That is an object that's pristine, chemically pristine, that is just emerging from darkness. Now, my book, was published following the successful launch of James Webb, and it gives a lot of the history of how we got to this point and the technology that has enabled all this amazing progress that has got us back to observing galaxies when the universe was only a few % of its present age. The story starts in California with the mighty Palomar telescope, which many listeners may have visited. It's a fabulous place. My own career began in Britain, and for many years, my telescope was the Anglo-Australian telescope, which was opened by Prince Charles, now King Charles, of course, in Australia. Britain then built telescopes in the Canary Islands. Then I emigrated to California, and I started using the Keck telescopes in Hawaii, as well as Palomar. And as you said in the introduction, I'm now back in Europe, and there's the European Very Large Telescope in the Atacama Desert in Chile. But these are ground-based telescopes. We measure the power of these telescopes by the size of their mirror. We, of course, have space telescopes too. Everybody's heard of Hubble. By the way, it's still operating. It's not been eclipsed by James Webb. It's still doing great stuff. The Spitzer Space Telescope has finished, but it was an infrared telescope. And it's, in a sense, its successor.
Just to interrupt briefly, that my colleague Nick Spitzer is the son of Lyman Spitzer.
Is that right?
He's at UC San Diego. Yes, he's.
That's amazing. Is he an astronomer then?
No, he's a brilliant National Academy member of a neuroscientist. But he has shared with me many recollections of his with seeing Einstein back at the Institute for advanced study with his renowned father. Yeah, sorry, but a little connection to space.
Yeah, well, that's very exciting. Well, Lyman Spitzer features in my book as one of the two heroes that led to the success of Hubble Space Telescope.
That's right.
So let me take you back to the 1920s, where this amazing man, George Ellery Hale, who was himself a distinguished solar astronomer, he had a knack for raising money from wealthy donors for a succession of what became the world's largest telescopes, the 60-inch and 100-inch on Mount Wilson, just outside Los Angeles, and here the beautiful Palomar Observatory, halfway between Los Angeles and San Diego. I'm a little romantic, really. Here's a picture from my encyclopedia from 1958 when I was a little 8-year-old boy. And I would turn back to this page many times. It's a cutout picture of a big telescope. It didn't say the name of the telescope, but it clearly is the Palomar 200-inch, as you can see from this nice photograph.
Oh, yeah.
And little did I know when I was 8 years old that one day in California, even that I would move to California, but one day I would become the director of this telescope shown in this encyclopedia when I was 8 years old. Now, Ellery Hale hired Edwin Hubble, and Hubble sadly had a heart attack just as the 200-inch was coming online. But he began a program to look back in time. This was, I mean, at Palomar, the whole concept of looking back in time unfolded. And as Hubble had this heart attack and died in 1953, he handed the baton to his disciple at the Carnegie Observatories, Alan Sandage, shown here, who passed away in 2010. And the idea was to use the 200-inch to measure the history of the cosmic expansion, to use the brightnesses of galaxies to measure their distance and to measure their redshift to tell us the velocities that they had from the expansion of the universe, and to see whether the universe was slowing down in its expansion as people predicted. Now, sometimes people think astronomers are, fairly easygoing people, but believe me, it's a competitive subject. And within the same city in Pasadena at Caltech was a rival to Alan Sandage, Jim Gunn, a younger man who's still with us, fortunately. And the two of them battled it out on this massive telescope. They were doing the same project, competing with one another. And then along came a woman, Beatrice Tinsley, a theorist, a New Zealander, who visited Pasadena in 1975 and demonstrated to both these famous pioneers, Sandage and Gunn, that, just as stars evolve and explode and change their colors and brightnesses as they grow old, obviously galaxies must do the same. So you cannot estimate the distance to a galaxy by its brightness. And this was a huge shift in the subject when I was a young postdoc. I just got my PhD, that we really are looking back in time, not to measure the rate at which the universe is slowing down, but to understand the galaxies themselves and to look back to their birth. And so that is really the theme of the book. And of course, I've lived through an amazing period where technology has made a huge advance in our capabilities. Firstly, these pioneers like Hubble, Sandage, Gunn, believe it or not, were using good old-fashioned photography. And it was really slow and hard work. Now, of course, we have digital detectors, such as the ones in our mobile phones, and these can be 30 to 40 times more efficient than the photographic plate. And so at a stroke, you can imagine having a telescope that's just 30 to 40 times more powerful by incorporating a digital detector. I mentioned that the size of a telescope is its power. The diameter of the mirror, 200-inch, is 5 meters. It was the biggest and most powerful telescope in the world for 40 years, but eventually it was eclipsed by 8-meter class telescopes and the twin 10-meter Keck telescopes. And then finally, the last sort of innovation really was what we call multi-object spectroscopy. You see, to measure the redshift of a galaxy and hence its look-back time, you need to gather the light, and Sandage and Hubble and others were doing this one galaxy at a time. If you could multiplex, if you could gather the light, as is shown here in this top panel on the left here, if you could gather the light of, say, 50 galaxies at once in the field of view of the telescope, which is this little square area here, with optical fibers, which is very much like optical plumbing, and gather the fibers and feed them into a spectrograph, then you can measure the redshifts of 50 galaxies in the time it takes to measure one, a huge step forward in the subject. Initially, this was done manually. This is me over here in the 1980s, plugging in fibers into a brass plate where the holes have been drilled at the precise positions of galaxies. But ultimately, we used robots to do this. And now this is big business. People are using robots to measure galaxies 5,000 at a time. So this was a huge revolution as well. Now, how do you select the galaxies that are the most distant, even if you still have to do the spectroscopy? And there's a very clever trick, which was first pioneered by one of my former Caltech colleagues, Chuck Steidel, and that is that the universe has a lot of hydrogen, not just in the stars and in the space in between the stars, but even in the space between galaxies. And hydrogen has a very characteristic absorption in the ultraviolet, and it cuts off the light. And the wavelength at which it cuts off the light is an indication, it's an approximate indication of how far away the galaxy is. So, for example, in this little picture from Palomar, you see a field of galaxies taken in a red filter, you see a field of galaxies taken in a green filter, you see it in the ultraviolet. But this particular galaxy circled here disappears. Excuse me a minute. And that's a hint that this object is very distant and that this absorption by hydrogen has been shifted so that this galaxy so-called drops out. Here's a little a cute movie that shows you these are all the color filters on Hubble Space Telescope. Mm-hmm. There's blue filters, green filters, yellow filters, orange filters, and red filters, and infrared filters. And the energy spectrum of this galaxy moves through, and you can see the redshift is going up and up and up, and hence the lookback time is increasing. And you can see in the pictures below that as the galaxy moves further away from us, it disappears respectively in different filters. So if you can see at which filter a galaxy disappears or drops out, then you get an approximate estimate of the lookback time to that galaxy. So, my book is also about the sociology of observing. Young people go to the telescope. It's inspirational to observe. I mean, it is possible, of course, to do it over the internet. And of course, practically speaking, during the pandemic, and if you are short of cash for going to the telescope, then the internet does offer the ability to observe remotely. But I think there's no substitute. I'm really a traditionalist. There's no substitute for going out of the office and going to the telescope, focusing on the task at hand. And it's inspirational to make a discovery in real time. And so going through some of the moments of joy is covered in the book. But of course, there are cloudy nights. This is a cloudy night photograph where, it's very depressing. This guy on the left here, his thesis is disappearing because he's had 4 cloudy nights in a row. And, so there are ups and downs in observational astronomy, just like in any other scientific discipline. So how far did we look with Hubble? Well, there are 2 ways of going as deep as possible. One is to point Hubble in a not particularly interesting area of sky and exposing for a long time. And this is one of those ultra-deep exposures. It's called the Hubble Ultra-Deep Field. It was taken by our team, where here we are at the University of Edinburgh. This is me and my co-investigator, Jim Dunlop. And the galaxies shown, if you can spot them with these colored squares with the numbers, are the most distant galaxies in this image. This field of view is about the 10th the diameter of the full moon. And there are about 3,000 galaxies in here. And via this color technique that we just discussed, these 6 or 7 objects are the most distant. And this particular one, we thought might be at a redshift of 11.9, which would be the most distant object ever seen with Hubble. The other technique, in addition to this sort of rather mindless just point Hubble and expose for a long time, this exposure, incidentally, adds up to about 10 full days of observation. The other technique goes back to that Joe Biden image where we look to a background galaxy, but we look through a foreground cluster that magnifies it. And this is a phenomenon that Einstein predicted called gravitational lensing. And it's like having a telephoto lens in the sky. So you look through this telephoto lens, and it provides an extra boost in power in finding these objects. So fortunately, these two very different techniques, pointing to a random area of sky, pointing through a lensing or magnifying cluster, do give the same result. And that is that as we go back in time to higher and higher redshift, to when the universe was younger and younger and younger, the number of galaxies that we see drops precipitously. For aficionados, this is what we call a logarithmic scale, and there's a factor of 1,000 from top to bottom. Now, with Hubble, we reach the end. This is as far as we could see with Hubble because we run out of filters because of the redshift and the stretching of light. And there was some debate in the community as to, what's going on here. If the number drops very steeply, as theorists like, then cosmic dawn was quite recent, maybe redshift 12 to 13. But if the number is going more slowly, then cosmic dawn would be somewhat earlier in cosmic history. This is already out of date. We have made such progress in just 6 months with James Webb. Before we turn to James Webb, there is one other trick, and that is you could go to a very distant object like this one here. And although you can't probe back enough to see objects like it forming, if you knew how old this object is, how old the stars in this object is, it would give you an indirect way. So the analogy here is you're walking down the street and you meet a boy. He's 4 years old, but you weren't there when he was born. But if you could find out how old he is, then of course you can indirectly estimate when he was born. And it's exactly the same. So we went to find this galaxy and we measured its redshift. This is in the Atacama Desert here. You can see it's a really barren place in northern Chile. In some parts of the Atacama Desert, it's not rained in recorded history, believe it or not. This is the European Very Large Telescope, one of the astonishing observatories, maybe the only large telescope with a swimming pool, I might add. We measured the age of this galaxy to be 290 million years, so it only formed after 250 million years after the Big Bang. We repeated this experiment for 6 objects, and just before the launch of Space Telescope, we predicted that cosmic dawn is a gradual process that occurred between 250 and 400 million years after the Big Bang. So here we are. This is this monster telescope. There's a human here. This is in the Northrop Grumman facility in El Segundo in Los Angeles, and I was very privileged to see it in February 2020, 1 month before lockdown. And you can see it's a segment, what we call a segmented mirror telescope. It has 18 segments. It's 6.5 meters from top to bottom. The mirror has to be folded to be launched. Each of these segments is made of lightweight beryllium, which is the lightest metal, and is gold-coated. It's gold-coated to improve its reflectance in the infrared. I was on the original committee in 1996. I was the only European-based member of that committee that proposed this amazing facility. At the time, it was called the Next Generation Space Telescope. So 21 years, hard work by 1,000 engineers, with many ups and downs, threatened cancellation, cost overruns. But then finally, this expensive facility is hanging here by a hook. Yeah. I mean, your heart would be in your mouth if you were there. And it's being transferred into the nose cone of this Ariane space rocket in Guyana in South America. Wow. Launched on Christmas Day, 2021. This is the last view that we will ever have of it, because it is not orbiting the Earth like Hubble. It is orbiting the sun in a very special place where the gravity of the Earth and the sun enable it to orbit with the same period as the Earth goes around the sun. And here's where we are. I'm at the end of the story. Here's that controversy that theory predicted that cosmic dawn would be at around a redshift of 12 or so. We have actually already, in the space of 6 months, probed much deeper to when the universe was about 300 million years old. We're seeing galaxies out to redshift 14. There have been claims even of galaxies at redshifts of 16. What the puzzle here is, I mean, I'm very pleased with this because we predicted there would be starlight out here from our observations of the ages of those galaxies. But there is an important discrepancy here, that the galaxies are much brighter than theory predicts. And we can discuss that. We don't know what is the cause of that. We are getting spectra of these galaxies now. I'm running out of time, so I'll speed up a little bit. That galaxy, the most distant one that we saw with Hubble, I was so pleased, 11.9. The spectrum confirms its redshift. It's a beautiful spectrum. We see chemistry. There's a galaxy at a redshift of 10 where the spectrum is so beautiful that we see the chemical elements: nitrogen, helium, carbon, magnesium, neon, oxygen, and so forth.
No.
So it is an amazing time, Brian. And, you know, we are optimistic that we will see cosmic dawn somehow, whether it'll be statistical or otherwise. And, you know, every telescope I've used in my career has done much more science than it was originally intended to do. And as I often say in my talks, you know, unlike politicians, astronomers deliver far more than they predicted. So it is an amazing time. So I'll stop sharing my screen, shall I?
Yes. Thank you so much, Richard. That's a real treat and a delight for my viewers, some of whom are quite young and deciding on what career path they may choose. We have a very, very young and be it, you know, fortunate or not, the mostly male audience, and
Yeah.
many of them are looking towards careers in the STEM fields. And
Yeah.
I think this type of presentation from one of the, you know, gurus and Svengalis of the field will help to convince not a small number of individuals that this is indeed perhaps one of the most important, significant, and exciting fields that one can go into. And I would only, you know, further buttress that with a call to the experimentalists like me who want to build the instruments and take part as well as the observers in the analysis of the data. I mean, the only thing I think that we observers and experimentalists don't do is come up with brand new theories, but we do have to, at least my students do, Richard. I'm interested in your educational philosophy. You've had, what, 100 graduate students or something, 1,000 papers, one of the most renowned. My philosophy of my graduate students is that they don't need to create new theories, but they need to understand the theory that underpins their field and adjacent fields. What's your educational pedagogical philosophy?
Yeah, I agree. And there's a lot of, you know, if you go back to Hubble and Sandage, Hubble was really an empiricist. He had no basic understanding of Einstein's theory. He actually, although it's claimed that he discovered the expanding universe, he never said he did. He never claimed the universe was expanding. And he was reluctant to learn the theory. And Sandage, who is in many ways my hero, changed his philosophy and said, I must understand the mathematics of Einstein's model of the universe if I'm to be a successful observer. And in my career, you know, we now have a model of the universe. It's called the cold dark matter model. It postulates that much of the gravitating material in the universe is dark. And I've had to learn from theorists like Carlos Frank, who was at Durham with me for many years, the fundamental aspects of that theory. So I agree, you know, just going out to the night sky and look and being inspired isn't enough. It really helps to have the physical basis of what people are saying. And that's why, of course, we go to scientific meetings. Yeah,
that's right. Yeah, and but also to capture for the professional set. I've been astonished through my career at how the paucity of basic astronomical knowledge is amongst my astronomical colleagues, even the observers. I'll have them over, we'll be talking in the night and maybe having a drink or something, and I'll say, "Oh, look up there. What do you?" They're like, "Don't ask me what that is. I'm an astronomer." And I'll say, "Oh yeah, I guess when we go to the geography department and I ask where's Mexico, they'll say, "Oh, don't ask me. I'm a political scientist." Yeah, I don't know where these things are. But for me, it's this visceral connection that you can do it anytime, anywhere. I've been to the South Pole, not at night because I'm not that insane, but I've been there during the day at the South Pole, which lasts 6 months, obviously. And the only astronomical object you can see is the moon, but you can see it, and the sun, but that's about it. And yet you could still do astronomy anywhere on Earth, any time of year. And to me, it's been the constant companion for my intellect throughout for the last 4 decades or so. But I want to ask you, in the book, you talk briefly about Fred Hoyle, who is, of course, a very close collaborator with Willie Fowler. Who was probably, I don't know, you didn't overlap with him, did you?
I didn't. I never met Willie Fowler, but I lived in his house in Pasadena. Can you believe that?
Gosh.
Yeah, we only found this out by accident. Yeah, but anyway, yeah.
So the Burbages, Jeff and Margaret Burbage, Titanic contributors to astronomical discoveries throughout the 20th century, the mentors to Vera Rubin in her first exploits into spectroscopy, and later go on to rotation curves taught by them, really. And even Jeff was a theorist, but he never, I knew him very well. I miss him greatly. He was irascible. And every time we'd have a cosmologist come to speak, the moment that person would mention, whether it was my colleague Asantha Kure or Adrian Lee, these are renowned professors in the UC system, they'd come to, and Jeff would sit in the front row. He was this jovial, large, big British lion. And Margaret was the opposite. She would never talk. She was so sweet and so quiet, but I don't think I ever exchanged 5 words with her in her overlap. But anyway, Jeff would harumph, and he would say, "Cosmology, Raleigh." And yet he would be very patient. He wouldn't dress down the speaker. But it's clear he always believed in the falsity of the Big Bang model until he died. And so much so that his colleague and Fred Hoyle's one of his best graduate students, Jayant Narlikar, who's been a guest on this podcast, if you can believe it, he, still maintains in the veracity of the quasi-steady state. What do you do with people like that? Or now the latest controversy is the Big Bang never happened, and that's proven by the rotation of spiral galaxies and their observation at redshift, 10, 11, 12, and that's impossible. Therefore, the Big Bang. How do you deal with otherwise, intellectually sane?
Yeah, you have to have an open mind. I know the young people, and I've seen, they're easily, drawn along by the standard theory, and it's very popular for young people to ridicule some old eccentric who, believes that we live in a steady state universe, or that the Big Bang model is incorrect or so. And often at conferences, somebody will stand up and make a case for some exotic model of the universe. And the young people often, roll their eyes and, put their heads down and so forth. But I think as scientists, we have to be professional, and we have to listen, and we have to engage in these people. So, I have met Narlikar, and of course Fred Hoyle as well. I met Fred Hoyle because he was a previous Plumian professor in Cambridge. And you've got to give them their moment to ask these questions. And the reason for that is occasionally, but very rarely, there's some truth in these crazy ideas. And the moment you stifle crazy ideas, then creativity is lost.
Mm-hmm. Well, Richard, you've been so gracious with your time and your materials. You've helped us look through a crystal ball into the future of where astronomy is going. But now I want to ask you one of my 4 patented questions that I ask all my esteemed guests when they come on the podcast. They're all 4 of them are related in one sense or another to the great Sir Arthur C. Clarke, another countryman who gave us is the namesake of the Arthur C. Clarke Center for Human Imagination, of which I am the associate director here at UC San Diego. And he said many things, and one of them is quite famous. We open the audio podcast with his actual voice saying the following. He's saying, any sufficiently advanced technology is indistinguishable from magic. I want to ask you, if you were to think about what the most magical technology ever invented by a human brain and human culture, what would you say it is?
In the whole of history, I would say the wheel.
Okay, very good. Not the filter
the wheel,
not the filter wheel, right?
Well, the wheel. Obviously, you begin with the wheel with carrying heavy things and leading to mobility. But the wheel then becomes an engineer's tool for lifting things and ultimately, for the motor vehicle and transport and airplanes and everything. So. It's the one thing. Now it's a functional thing. It's not something that improves health but it's a difficult choice. Yes, what's your next question?
Yeah, the next question is another quote from Sir Arthur C. Clarke, and that is the following. When an elderly but distinguished scientist says something is possible, he or she is very probably right. When he or she says something is impossible, he is most certainly wrong. What have you been wrong about, if anything, over your career?
Well, often we claim that these galaxies are at these extreme distances, and the literature is riddled with mistaken objects. An object that people got excited about as the most distant galaxy. And I'm not I want to emphasize that I'm just like everybody else. I've fallen into that trap too. Mm-hmm. And so sometimes in your own enthusiasm to make a discovery, you can say that something is believable when it's marginal. So the way we talk about this in science is the significance of an observation. If an observation is noisy, but you feel that, in your heart that the observation is exciting, then it's possible to write a scientific paper where you say, well, I'm not 100% sure this is correct. But if it is correct, it's a revolution in the subject. And there's many ways in which you can write such papers. And I've been guilty of doing that just like everybody else.
Yes, it's almost reminds me of what's called the Banister effect, where Roger Banister was the first to break the
4-minute mile.
4-minute mile. And then everyone after that has done it, and so it's like, well, what if we, raise the age by one more year? Do we get, to write a famous paper? It's kind of like pharaohs would be buried with all their treasure. I guess we all human beings want to have a mark of our own. Richard, the last question has to do not with looking forward through a crystal ball through this type of lens, but looking through one of these lenses and looking into the past. As you said, telescopes are time machines owing to the finite nature of the speed of light. We're talking now, we have a little bit of a delay between LA and San Diego. We hear voices on the moon. We see images from Hubble and from the James Webb. These are delayed. I want to ask you a question. As Sir Arthur said, he said, the only way of determining the limits of the possible is to go beyond them into the impossible. And that's the origin of the name of this podcast. I want to ask you as well, Rich, I want to ask you, looking back through a telescope of time, what mysterious aspect of your life, your career, baffled you? And what advice would you sort of give to that 20-year-old self in order to give him the courage to do as you have done, to go into the impossible?
Well, I think I lived at a very interesting time where there was adequate funding, firstly, for bigger telescopes. Technology went through a revolution. The digital detector, the robots that I mentioned, making bigger mirrors out of segments rather than trying to make single glass mirrors. So technology is the advance. And I think when I also, and as I discuss in my book, I actually raise money for these technological developments. So I would keep my eye open for an interesting new twist in technology. And I would think, gosh, this would really transform astronomy. So I think just plodding along and using the same telescope, and trying to do better work with the existing equipment is never enough. You have to be interested in the instruments themselves. And most astronomers are not. You'd be surprised. Most astronomers regard it's like going to the supermarket. They say, what's available? I'll go in there. Oh, I can use this. I can do that. What about designing your own supermarket? And that's, I'm proud that that's what I did. I managed to couple my enthusiasm with an interest in technology. Even if I wasn't an engineer myself, I would find an engineer and I would say, look, if you work with me, we really make discoveries if we can do it this way. And that's a feature of my book as well, the partnership with technology.
Yeah, I love the aspect of it. That's it's a memoir. It's not only an elucidation of the most fascinating, in my humble opinion, branch of all of science. Richard, I pointed out in the first class that I gave in my Cosmology Physics 162 here at UC San Diego a couple of weeks back. And greetings to all my students. I'll see you soon, as I will begin teaching soon. The Wikipedia entry for all of science, if you go to Wikipedia and type in science, I'll leave this as a homework exercise for the reader and watcher, and type in science, you will see a picture of no other branch of science other than what Richard and I have been discussing for the last hour. And that's a testimony to how important, both historically and for the present and future development of not only ideas, but also technology. So Richard Ellis, phenomenal discussion, wonderful book. Congratulations on both. I wish you safe travels back to the UK, and I hope to meet you in person one day over there or over here.
Thank you very much, Brian. It's been a pleasure.
Any sufficiently advanced technology is indistinguishable from magic.